Good morning, everyone. Today we're going to discuss Experiment 2, Determining the Hardness of Water by Titration with EDTA. We will cover the fundamental principles, the experimental procedure, and the data analysis required. The main objective of this experiment is to understand the principle of EDTA complexometric titration, the color-changing behavior of iriochrome black tea indicator, and to learn how to determine calcium ion concentration in an unknown sample using a standardized EDTA solution. This experiment is very important in analytical chemistry because water hardness analysis is widely used in environmental chemistry, industrial water treatment, and quality control. Hard water contains calcium and magnesium ions. There are two types of hardness. Temporary hardness is caused by calcium and magnesium bicarbonates and can be removed by boiling. Permanent hardness is caused by sulfates and chlorides of calcium and magnesium and cannot be removed by boiling. EDTA stands for ethylene ediaminate acid. It is a hexadentate chelating agent, meaning it has 6 donor atoms that can coordinate with a metal ion. EDTA is a 4-proton weak organic acid, and depending on the pH of the solution, it can exist in different ionic forms. In this experiment, we used disodium EDTA, which reacts with metal ions in a 1:1 molar ratio. This property makes EDTA very suitable for quantitative analysis of calcium and magnesium ions. Now let us understand the role of the indicator iriochrome black tea or EBT. EBT is used as the indicator to detect the end point of the titration. The color of this indicator depends on whether it is free or bound to a metal ion. At a pH between 7 and 11, the free indicator exists in the form hydrogen indicator ion, which is blue in color. However, when EBT binds with metal ions such as magnesium or calcium, it forms a metal indicator complex that appears red or wine red in color. So initially, when metal ions are present in the solution, the indicator binds with them and the solution becomes red. During titration, EDTA is gradually added. Because EDTA forms a stronger complex with metal ions than EBT, it will remove the metal ions from the EBT complex. As a result, the indicator is released back to its original form, which is blue. Therefore, the color changes from red to blue, indicating the end point of the titration. There is an important detail about the indicator. When EBT is used with magnesium ions, the color change range matches well with the titration equivalence point. This means the color change is clear and easy to observe. However, when EBT is used with calcium ions alone, the color change is not very clear because the equivalence point does not fall within the color change range of the indicator. To solve this problem, we add a small amount of MgEDTA complex to the solution. This provides magnesium ions that form the red MgEBT complex, making the endpoint more visible. Following equipment and chemicals required for this experiment, the main instruments include a burette, pipette, volumetric flask, beaker, and conical flask. These are used for preparing solutions and performing the titration. The important chemicals used are disodium EDTA, calcium carbonate, ammonia buffer solution at pH 10, iriochrome black tea indicator, and MgEDTA solution. These chemicals help us determine the calcium and magnesium ions present in water. Now let us move to the experimental procedure. First is the preparation of EDTA solution. We weigh about 3.5 grams of disodium EDTA and dissolve it in about 50 milliliters of deionized water in a beaker. Sometimes, gentle heating is needed to help it dissolve completely. After the EDTA is fully dissolved, the solution is transferred into a 250 milliliter volumetric flask, and the volume is adjusted with distilled water to the mark. This gives us the EDTA solution used for titration. Next is the preparation of the calcium carbonate standard solution. We weigh 0.4 grams of calcium carbonate and place it in a beaker with about 20 milliliters of deionized water. Calcium carbonate does not dissolve easily in water, so we add hydrochloric acid slowly, drop by drop, until the solid completely dissolves. It is important not to add too much acid. Usually about 1.5 milliliters of HCl is sufficient. After the solid dissolves, the solution is transferred into a 100 milliliter volumetric flask, and the volume is filled up with distilled water. This solution will be used as the standard solution for calibration. Now we perform the titration step. First, we pipette 25 milliliters of the calcium carbonate solution into a flask. Then we add 2 milliliters of pH 10 ammonia buffer solution. This buffer is important because EDTA complexes with metal ions more effectively in an alkaline environment. Next, we add 0.5 milliliters of EDTA solution, followed by about 4 drops of the EBT indicator. At this stage, the solution should appear wine red because the metal ions are bound to the indicator. Then we start titrating with the EDTA solution from the burette. As EDTA reacts with the metal ions, the red color gradually fades. At the equivalence point, the color suddenly changes from red to blue. This color change indicates the end point of the titration. To obtain accurate results, the titration should be repeated 3 times, and the average value should be calculated. After calibrating the EDTA solution, we proceed to determine the calcium content in an unknown sample. The procedure is almost the same. We take 25 milliliters of the unknown solution, add the pH 10 buffer, EDTA, and EBT indicator, and then titrate with the standardized EDTA solution until the color changes from red to blue. Using the titration volume and the concentration of EDTA, we can calculate the amount of calcium ions present in the unknown sample. After finishing the titration, we first record the volume of EDTA used from the burette for each trial. Since the titration is performed 3 times, we calculate the average volume of EDTA to reduce experimental error. Next, using the known concentration of EDTA, we calculate the number of moles of EDTA used in the titration. Finally, let us discuss some important precautions. First, hydrochloric acid must be added slowly and dropwise when dissolving calcium carbonate to avoid excess acid. Second, only 4 to 5 drops of the EBT indicator should be used. Too much indicator can affect the clarity of the color change. Third, you should try with deionized water to observe the color change of indicator. Fourth, all glassware such as the burette, pipette, and volumetric flask should be rinsed with distilled water and the respective solutions before use to avoid contamination. Fifth, also, remember that the complexes formed between EDTA and metal ions are colorless. This slide presents some discussion questions related to the experiment. These questions are designed to help us understand the reason behind some important steps in the procedure. The questions focus on why hydrochloric acid is added when preparing the CACO solution, why an alkaline buffer is required during the titration, and why EDTA is added to the solution. These questions help students review the chemical principles involved in EDTA, titration, and the determination of calcium in the sample.